This is the Earth Science Classroom. Welcome back to the channel. This video is in the Atmospheric Science playlist. It is one of the Atmospheric Science review videos, reviewing the material and content for the upcoming test. This video in particular is looking at GCMs, which stands for General Circulation Model, which is basically looking at how the whole Earth heats up in different areas and how that creates different circulation and convective cells in the troposphere to transport and move heat across the Earth from the equator towards the North and South Pole, and all the different winds and pressure belts and low and high pressure zones that are created because of this differential heating at the equator. And we'll look at all the different processes that go along with that.
Part 1. Earth's differential heating.
So to look at GCMs and how the atmosphere moves as a large system, we've got to break it down into how this starts and how this initiates. Now, this is called differential heating. Differential heating is how certain areas of the Earth or locations are heated more than other areas. So this is a great example of how the Earth is tilted. On the axial tilt inclination, which is 23.5 degrees currently, it does fluctuate, but we have this tilted Earth. This is the cause for the seasons in various latitudes, and the seasons get more pronounced and more diverse with the 4 seasons in the mid-latitudes compared to the more northern latitudes and southern latitudes towards North and South Pole, or towards the equator where these seasons are minimized, or there's only 1 or 2 seasons. So I have this red line showing the equator, which is 0 degrees latitude, and it's at a tilt, an angle, because of the actual tilt, and the Earth spins from west to east, and this gives us our 24-hour day and how the Earth rotates on its axis. So the Sun, which is over here on the left, it gives us the solar constant, which is the general average amount of energy the Sun puts out that we, the Earth, receive as a planetary system. The energy and EM spectrum and radiation, that is all coming at us, and we receive this energy, and the atmosphere receives it first, and then obviously the surface, both the oceans and land, receive it afterwards. And we do give off some energy, which we know is called albedo. But the energy we keep is what we look at, because the energy we keep in the atmospheric system and the Earth system, the oceans and land, that is what drives our GCMs, our general circulation models in the troposphere and how heat is moved. So around the equator, you have this very direct area that I'm marking out with black right here, that when the radiation hits this area, because the shape of the Earth is an oblate spheroid, it's a sphere, it's a bit fatter around the equator than it is from the north and south, as an up and down. So because this radiation arrives at the Earth in straight lines, the angle at which it hits the equator is close to 90 degrees, as in a right angle triangle. So therefore, the radiation, the energy from the Sun, is hitting the equator or the equatorial region at a very direct and concentrated area. So the amount of energy, the solar constant that's hitting the equator is direct and concentrated, therefore it will become hot. Now the same energy that is traveling through space and hitting the North and the South Pole at the same time is not having the same effect, because the shape of the Earth is a sphere. And you'll see that the area that the energy is hitting is angled. The energy is going to be spread out over a much larger area in the higher latitudes towards the North Pole, and the same spreading out of energy in the South Pole. That means that there will be less concentrated energy because it's spread out over this larger surface area compared to the equator. And the same thing up here, so it's less concentrated, and therefore it becomes colder because it's less thermal energy because it's being spread out, therefore it's colder. That's why generally the North and South Poles are of a lower temperature than the equator. So what we have here, because of the Sun's radiation coming in and received by the Earth in a straight line, and the Earth being curved, the surface being curved as the energy is hitting the Earth, it's going to distribute the energy and the heat, so it creates this differential heating. whereby the tropics and the equatorial region is warm and hot versus the polar regions, which is generally colder. Now, the area in between 30 degrees north and 60 degrees north and south of the equator, this area is called the mid-latitudes. So generally there is a mixture of warm and cold air mixing in these locations, causing a lot of the variety of weather we see with mid-latitude cyclones, tornadoes, and hurricanes do start and originate in the tropics, but then make their way into the mid-lats to make landfall in certain areas. So the key is to remember that the equator is hot, the poles are cold because of the Earth's shape and because of the receiving radiation from the sun in straight lines or photons and it being concentrated through different surface areas. So the equator is concentrated and the poles is spread out.
Part 2. Atmospheric pressure.
So as a recap of what atmospheric pressure is, so we're dealing with gases. So atmospheric gases are variation between nitrogen, oxygen, argon, and trace gases, which include water vapor. Now, the gases have a molecular weight, both individually and as a cumulative addition of all the atmospheric mass. Now, this mass is acted upon by gravity and gravitational forces, and it is brought down towards the surface of the Earth because gravity is a force of attraction towards the center of our planet to the center of the mass. So our gravity is going down towards the center of our planet, which involves bringing the air, which includes the air molecules, which we discussed, down towards the surface. So around 99% of all the mass, or the air molecules in our atmosphere, is within the first from the surface, which is 0 kilometers, up to around 50 kilometers, which is our stratopause. Basically meaning that the troposphere and the stratosphere contain pretty much all of the atmospheric gases and the mass. So the weight, which is gravity plus the mass, the weight, which is the force applied to an area, which is the air pushing down on the surface, this creates a certain amount of weight that in each area can be recorded. And for this purpose, we're going to use millibars as our atmospheric pressure unit of choice. You can use Newton meters or kilopascals or pascals, but we use millibars in this case. And this creates an average pressure of 1,013 millibars on the surface as an average, caused by gravity and the weight of the molecules pushing down through gravity on the surface. Now, in addition to what it is, we have to look at how it changes. So the average is 1,013 millibars, but across the surface in different locations and different geographic areas, we have a different pressure value at the surface. We're talking about surface here, because if we look at our surface, there is a consistent theme whereby the pressure is the highest by the surface, which again is 1,013, which is the average. But as you increase in altitude and you go away from the surface against gravity, so to speak, the higher you go, the less air molecules there are, therefore the less atmospheric pressure there is pushing down on a certain area or certain altitude. So as you start at 1,013, by 1 kilometer up, you've gone down to around half of the pressure. And then 2 kilometers, which is not really that high, you're looking at 300 millibars. And 3 kilometers, 4, 5, you're getting less and less and less air pressure, up to the point where towards where space is, which is considered between 100 kilometers on average, you're looking at 0.0001 millibars of pressure at around 100 kilometers, which we define really, or NASA defines as what space is, or the beginnings of space, where you are technically leaving the atmosphere. There are some air molecules there, but really not enough to distinguish an actual atmosphere. And this will be in the thermosphere, going towards the space station and up towards Hubble. So let's go back to why there is different pressures. There's an average, but different pressures. So you have our surface and you have our incoming solar radiation, and it heats the surface. And there is convection, and there's also radiation, convection, and conduction. And the surface is going to heat the first or bottom layer of our atmosphere, which is the troposphere. And with heat comes rise in air. And then you get what's called adiabatic heating, where the air is going to change pressure, therefore change temperature. But the surface heats the air is going to rise. So this rise in air would lower the air pressure at this particular location or location on the surface geographically. And if some air is rising, then we have to have an area, because that's to balance out within the troposphere, where the air is sinking. So there is an area of rising air, which would make the pressure lower, so lower than 1013 millibars. And then there's an area that's going to have air that's descending or sinking, which would add more air pushing down on the surface. So this would increase or raise or increase the atmospheric pressure on the surface at that particular location. That would be above 1013 millibars. So it could be included, or it could be also included there. So lower air pressure could be anything between 1,000 to 875, which is an extreme cyclone. Or air that's rising, air that's descending and causing higher pressure could be anything between 100 and 1,020 up to 1,050, so a very high pressure. And this can change the atmospheric conditions based on what the pressure is doing, and everything else kind of follows. So we have our low pressure diagram on the right here. Air is rising through different processes. So the air can be lifted through heat, through orographics, and also through convergence. And the last one can be lifted through frontal. So the four main types of lifting air. When you lift air, you're going to make air rise up, and you're going to lower the pressure at the surface. So generally, when you lower the pressure, you're going to have a movement or a cycle or a force in the air to move into the area where the air is rising. So you have wind, which is a bunch of air molecules moving in the same direction, caused by a difference in pressure, which is caused by a difference in temperature. This wind will bring in air from around the outside of this low pressure towards it, so we call it like a vacuum cleaner, where the air is being sucked up through these different processes, these different means, to a higher elevation, and this will cause adiabatic cooling, where the air changes temperature caused by a difference in pressure, so it gets colder and colder and colder the higher you go, with less air pressure as well. But the low pressure right here, which will be below 1013 millibars, would suck in the air, and we call it the vacuum cleaner. It's going to bring air up. When this happens, the conditions obviously change. The main one is when you make air rise, it's going to cool down adiabatically. It's going to sometimes it contains water vapor. If that air mass comes off a source of water, where you have evaporation, you have water vapor, and the cooling down water vapor will form condensation at the dew point in LCL and start to stimulate cloud formation, and you get different types of weather which involve clouds. You have weather but blue skies, but clouds, and you have different systems of clouds and different systems of precip and function of the amount of water vapor, the heat and the wind and wind shear, and from this we can create all of the different systems of clouds and weather that we can observe and study, things like rain and sleet and snow and thunderstorms and lightning, tornadoes, hurricanes, you name it, all comes from low pressure. Low pressure is the key and the starting point of making air rise that will cause the other weather systems to be created, to be formed. So on the flip side, we have higher pressure. So it's pressure that's going to be above 1013 millibars. Now, as you see this, we have air that is descending, air that is sinking and falling back down through difference in density. So colder air up by the pores, which is between 10 to 15 kilometers in the air on average, the colder, denser air is going to sink down. As it sinks down, it's going to heat slowly through adiabatic heating, which means as you go down towards the surface, we increase in pressure, which would also increase our temperature of our air parcel. Now, this high pressure air that's sinking and pushing down, it's pushing down on the surface. In addition to our lovely gravity, you're going to have a higher air pressure, which is the opposite to our lower pressure, where air is leaving the area. And we're discussing the area around the surface. Now, yes, we have gravity, perhaps you have the ground that's heating the air, but generally you have this overall sink in air even if the ground is going to be heated. The high pressure overpowers the heating and rising. So this high pressure could be anything around like 1050 whatever or 1060, but you have this higher air pressure and you see the air has to go somewhere. With low pressure it was being drawn in and sucked up, whereas this diagram the air is being pushed down and it can't go through the surface because it's air. I mean, some might go into the soil or the ground or the first few layers of the Earth's surface, but generally the majority of the air is forced to go elsewhere. It can't go back up, can't go down, so it gets forced to the sides and flows parallel to the Earth's surface, which we call surface wind. This surface wind will then eventually move and connect and be sucked into an area of low pressure. So the high pressure, the conditions that we expect from high pressure is stable atmosphere, which means the atmosphere hasn't got a tendency to rise and move up higher altitudes. It has a tendency to stay where it is, it stays still, or it has a tendency to sink down to a lower altitude. Now, why is this important? Well, because if you heat the air adiabatically and you lower the altitude, you're not going to stimulate any kind of condensation. So condensation does not occur because you need water vapor to cool down to a lower temp to force condensation and a phase change back into water. So if you raise the temperature of the air, make it hotter, the water vapor inside the air maintains and stays as water vapor. It doesn't condense. So if you have no condensation, you have no cloud formation, you have no weather systems which involve clouds, what do you have? You have lovely blue sky, which is beautiful where you are, Australia, Asia, Africa, North America, Europe. You know, I'm from England, so we rarely see blue sky. And we do see blue sky, we treasure it and wonder when it will go away. And it usually goes away in the same day with some cloud formation. But that's just England. So the blue sky is the absence of clouds because clouds can't form because air is sinking. And you have this beautiful, stable atmosphere. And for a short time, especially in England, you get a beautiful sunny day. So when you combine these two different pressures, high and low, based on the movement of the air caused by changes in temperature, which causes the eventual change in pressure at the surface, you have the high pressure sinking and the low pressure rising, but across the surface you have this wind that is generated to move the air from the high pressure towards the low pressure to complete the cycle. And above at the pores, you also have air moving horizontally parallel to the surface, and that goes from the low pressure because it has to move up, can't go any further than the pores. You have this air moving towards the high pressure and then sinking due to density and forming the high pressure in the air that's going to descend. So look at this big map on the right hand side. I've kind of connected a couple of these high and low pressure areas or zones or belts, and we could use, like, let's say geographically, so this would be 0 degrees or the equator in terms of latitude, and then we have 30 degrees north and south, and the same 60 degrees north and 60 degrees south. So you have this combination and kind of alternating pattern of high and low pressure across the Earth's surface caused by the initial, in this area here, the initial heating of the equator and the tropics, stimulating this low pressure air rising, and then having this movement of air either side to fall down and descend at 30 degrees, creating the Hadley Cell, and inside here the Ferrel Cell, and eventually over the poles, the polar cell. But you have this connected system of winds that are joining the high and low pressure together along the surface to either push air away or suck air in. So the high pressure I would call the leaf blower. Going to blow stuff on the surface away, and then the low pressure would be our vacuum cleaner, and that would suck in air up to high altitude. So this combination of high and low pressure moves heat around the surface and around the atmosphere, namely the troposphere, which this is showing, but also is going to stimulate wind systems on the surface and create different conditions in the atmosphere based on stability, which is low pressure is unstable So air is going to rise freely, and high would be more stable and be more consistent air. So high pressure we associate with nice, calm, light winds, blue sky. Low pressure we associate with all different weather systems, cyclonic systems, mid-latitude cyclones, frontal systems, cold front, warm front, storms, and basically any forms of precip.
Part 3. GCMs and the formation of the Hadley Cell.
If we take a closer look at the equatorial region around the equator, and we take our curved spherical Earth and make this section flat, so we can see this in a profile or a flat projection, as opposed to try and do it as a sphere. Now we have the equator right here. We have 30 degrees north and 30 degrees south, and in between we have the tropics, and we know this area is hot through the concentrated area and directness of solar energy, and it being more consistent all through the year. So the sun's radiation comes down. So the absorption of energy happens here in the tropics through concentrated energy and direct angle and being consistent all year round. So you have this first stage of thermodynamics, which is our conduction. The air is going to touch the hot surface, be it ocean or land, and conduct the energy, the thermal energy, into the air. And we have this air that's going to start to rise. So you have the hot air through conduction, and it starts to rise up through hot air rising, through density and buoyancy. And we have our hot air rising through different altitudes, because the troposphere is between 12 to 15 kilometers, and this dashed line represents it, and the average temperature of the troposphere is looking at minus 60 degrees. So the pause is where the change in temperature behavior happens, and then the stratosphere begins. But we're looking at the troposphere, so this is the troposphere as our area to look at. So this rising air, this hot rising air, will increase in altitude, obviously due to pressure changes and a less pressure. As you increase in altitude, you're going to have a decrease in temperature, and that is caused by what's called adiabatic cooling, because there's no longer any more heat source up here. The heat source is down the surface with conduction. So as you go higher up, this air is going to progressively lose temperature and decrease in temperature as it goes higher up until it gets to a point of minus 60 at the pores. Now this air, being so cold, cannot sink right down because the hot air rising is too powerful and too consistent. So the air must go somewhere. Don't forget, this is a dynamic and fluid environment of gas moving all the time. So if we can't sink and go down towards the surface right over the equator, it's going to be moved north and south. So we move north and south. This colder air is going to be moved or pushed to the side, north and south, and it will get to around 30 degrees or above this latitude, south, and 30 degrees north, and it will be able to sink because it's far enough away from this rising air over the equator. So this cold air that is very dense is going to sink down over the latitude of 30 degrees north and south. So we have this sinking or descending air either side of the equator at 30 degrees north and south, and it's going to come down towards the surface, and it's going to be pushed either side because the air cannot go through the ground, obviously being solid rock or ocean. Some might diffuse in the ocean, but majority can't go through, and it's then pushed either side, again, north and south. If it goes towards the equator, you get this surface wind being created to complete the cycle of moving air from hot to cold. So we have our beautiful convection of hot to cold, circulation of thermal energy, and this complete cycle we call the Hadley cell. And it is symmetrical, so it's the same on both sides, and we have this Hadley cell being formed through rising air over the equator and sinking air from the pores down over the 30 degrees north and south. And we can also link in our atmospheric pressure into this. We'll get into that later on.
Part 4. GCMs and the formation of the Hadley, Ferrel, and polar cells within the troposphere.
So if we expand this system, we have the initial catalyst or engine for our global circulation model, or a GCM, for the entire planet in the troposphere. You have the Hadley cell, two of them, symmetrical either side of the equator, being formed by convection cells for hot air rising and cold air sinking. Now it rises over the equator, which is 0 degrees, and it sinks over 30 degrees south and north, thus creating the first complete cell. Now I have drawn this arrow that is then leading off towards 60 south, and this arrow leading over towards 60 north. Now this is the initiation of a second cell that is next to the Hadley. So if we carry this on, we have the air that's going to move across the surface, the wind, and it's going to rise at 60 south. It's going to rise up again towards the pores, and again, same situation happens. Like the equator, it can't go any higher because it's too cold, and it's going to be moved, meet and collide and converge with this other part of the Hadley cell, and rather than going forward, because it can't go forward or higher, it has to go down, cold, and it's going to sink and rejoin, and this is called the Ferrel cell. That's next to the Hadley cell. So we can do the same thing over here on the northern hemisphere. The wind approaches 60 north, it's going to rise up. It's going to rise up towards the pores. It's going to split, and it's going to split over here in the southern hemisphere as well. And it's going to rejoin the Hadley cell here at 30 degrees north and sink because it's very cold. And we have our Ferrel cell over here. So we have our symmetrical cells forming because of air that's either being heated and rising, or it's cold with less heat and it's going to sink. And there's a final cell between 60 south and 60 north and 90 north and 90 south. And this is the polar cell. So we're going to have this situation where the air is going to sink again. It's very, very cold. And it's going to sink down towards or over 90 south. It's going to come back around across the surface as wind and rejoin at 60 and rise up. So we have a rise in section right here over 60, and it's going to sink down. This very cold air is going to sink over 90 south, which is the South Pole, Antarctica, and the same thing's going to happen over here in the northern hemisphere. So it's going to sink down, very cold, over 90 north. It's going to sink, and it's going to hit the surface and be pushed back and rejoin at 60 north, which is going to rise up. And we have our polar cell in the northern hemisphere, polar cell in the southern hemisphere. So again, we have a symmetrical set of 3 cells, Hadley, Ferrel, polar. So the simple heating and cooling of air in the troposphere from the equator, because the equator is heated more than the poles, and you have this differential heating, you have these 3 symmetrical convective cells that form in the troposphere called the Hadley, which is around the equator, the Ferrel in the mid-latitudes, and the polar, obviously in the polar regions, that form to move heat, and that requires air. It's going to carry the heat in the form of wind, and wind can be across the surface or can be up by the pores. And you have this rising air and sinking air based on density, and whether it's being forced up or encouraged up with heat, to create these 3 cells over the Earth's surface. Now the reason why the pores is there, and it's kind of like a dividing area between troposphere and stratosphere, is because the cold air towards the pores is very, very cold, and cold air cannot rise. So that's like an unofficial boundary that's separating the troposphere from the stratosphere. I add in the surface winds and also the upper level winds. So these lateral arrows that represent the wind in between the cells that connect the rising air with the sinking air. And what happens is the difference in temperature will cause the air to rise or sink, which will then in turn cause the area to have either a low or a high pressure. Now the wind is air moving between pressure zones. Now the high pressure is going to move the air away, and the low pressure will drag or suck in the air towards it. So there is a balance between low and high pressure, which is causing air to move between the areas of pressure caused by temperature difference. And this wind is what we experience on the surface, which is like the trade winds or the easterlies or westerlies. So this will be in the next video, but this is the Hadley, Ferrel, and polar cell, which is our GCM, which is our general circulation model.
Part 5, the formation of pressure belts and global winds.
So as a starting point, you in the classroom have this diagram given to you, and we started working on the Hadley, Ferrel, and polar cells as these 3 convective cycles or cells in the troposphere from the surface to the tropopause, which is roughly between 12 to 15 kilometers in the air, and the average temperature is minus 60 at that altitude. So looking at the movement of air and heat from the equator towards the north and south poles through this first layer of the atmosphere, the troposphere, and these three cells are the mechanisms that are going to transport heat through wind and air moving across large areas of surface, both ocean and land. So as shown on the diagram, these are the three cells. Looking at the red cell, which is the Hadley cell between 0 degrees the equator and 30 degrees north and south. So it's a mirror image, it's symmetrical either side of the equator. Hadley cell of rising air over the equator, moving laterally north and south towards 30 degrees north and south, and then descending through cold air and sink back down to the surface and recycle back to the equator. Then you've got the Ferrel cell in green, which is a parallel next to the Hadley cell system or function or cell movement, and the Ferrel cell is rising at 60, coming back to 30, sinking at 30, and there's a surface wave again along the surface between 30 and 60 degrees north and south of the equator. Then we have the polar cell, which kind of finishes up the three cells. Polar cell around the polar regions, north and south. At 60 degrees south, it's going to rise, like with the Ferrel, and then circulate back down, sink over the south and north pole, which is 90 degrees south and north, and then recirculate across the surface back to 60 south to then again rise again. So the three identical cells that are 3 in the northern hemisphere, 3 in the southern hemisphere, and these are symmetrical. So now you add in the pressure belts. These are consistent areas of low or high pressure around the Earth caused and created by these convective cells. So this is surface pressure. For example, the equator or equatorial region, which is around the equator, between 23 degrees north, 23.5 degrees south, you're going to have this low pressure, this consistent low pressure with air rising due to convective forces and it being constantly hot and concentrated energy around the equator. Hot air rises. So this low pressure is going to be consistent around the equator. Then we have the two belts of high pressure either side at 30 degrees north, where you have the descending or sinking air at 30 degrees north between the Ferrel and the Hadley cell, and you have this persistent high pressure of air sinking around 30 degrees north and south. Then we have the low pressure at 60 degrees north, which is again showing how air is rising between the Ferrel and the polar cell right here, and the same down here in the southern hemisphere where the air is rising at 60 south, and you have these belts or consistent zones of low pressure in this part of the world. Then we have the two polar regions, which is high pressure. So the southern pole, the South Pole, Antarctica is high pressure, air is sinking down. This part of the polar cell, and likewise in the Arctic, the North Pole, 90 degrees north, you have high pressure because the air is descending right here. So these pressure belts, which are consistent across the parallels, which are these lines here called parallels, and they are always there all through the year. And I also add in that the tropopause is the extent of these cells in troposphere, which we're looking at. And this is a three-dimensional system. I've drawn it on the side, but really this is happening all around the Earth in a 360-degree version, and you also have the Earth spinning and on a tilt as well. So there's a complex and dynamic function here. I've drawn it in this 2D version to show you exactly what's going on. So if you focus on the equatorial region to begin with, around the 0 degrees, the equator, this low pressure I stated, we have the winds. This red line here, this red arrow here and here, this is showing us the surface winds. I've extended them across the picture, across the diagram, and they are diagonal in this direction. Now, this is for a reason, which is both the Earth spins and we have what's called the Coriolis effect, which is making these winds deflected and move at a certain direction. But the low pressure is our vacuum cleaner. It's sucking in the air and sucking up the air to rise. So the air is being sucked in towards the low pressure belt, and it looks like this. Now, these winds are called something, we'll get to that in a second. Now, the low pressure where the wind is sucked into is called the doldrums, and it's also called the ITCZ, which stands for the Intertropical Convergence Zone, which is basically saying that in this area, this zone, that's tropical, between the tropics of Cancer and Capricorn, you have a convergence or coming together of air, which we see here with these two arrows that are converging, colliding, and going towards each other, towards this central equatorial line right here. Now I've added in more winds to fill in the gaps both in the mid latitudes between 30 and 60 degrees north and south, and also the polar regions. So we have this high pressure at 30 degrees north and 30 degrees south. Now this high pressure is our leaf blower, which is going to move the air or blow the air away from this location as it comes down from the tropopause, as seen here, and this causes the winds to move away. Also, we discussed how the winds move away towards the equator and recycle back within the Hadley Cell and causing the ITCZ, but also they move away from 30 towards 60 degrees south and 60 north towards that low pressure system, and these are angled in a certain direction as well, these green arrows. So they're angled in a certain direction. Then we have the 60 degree north and south low pressure, again where air is rising, the mix of the Ferrel cell and the polar cell as they collide and converge. You have the converging airs of the polar and the Ferrel cells, the mid latitudes. And you see this by the blue and the green arrows pointing towards each other and going towards each other. Again, the blue polar winds are angled at a certain directions, so make sure you have those in as well. So you should be following along with this video and adding in your arrows and your labels to your own diagrams, so the diagrams you have look like mine on this screen. So around the equatorial region, we call this the doldrums. Now the doldrums is an old English word that originates from an area being very dull, very uninteresting, very boring, and also is linked to the word tantrum. So why would you call this area dull and boring? When the 16th, 17th, and 18th century explorers and sailors would travel across mostly the Atlantic between the old world, being Europe and Africa, to the new world, being the Caribbean and newly discovered North America, since 1492 and Columbus, you had the movement of people in boats, sailboats, going across the Atlantic from east to west and west to east. And when they traveled across the Atlantic, they found that when they went across the equator, mode of transportation is a boat and a sailboat for that. And once they pass over this equatorial region, they found the wind died down and the boats couldn't move. So what happened was, in this diagram, you have the boat over the equator on the ocean, and the wind is being drawn up by the low pressure. So the actual wind across the ocean surface is basically gone. It's been sucked up in this low pressure system of the Hadley Cell on either side. So a boat that's going through this, let's say, 300-mile span of ocean over the equator has no wind to move or propel itself across the Earth's surface. So basically stops and is now just stuck in this area of no wind, no way of kind of moving the boat, and just at mercy of the slow ocean currents. So these ancient sailors back in the 16th, 17th, 18th century used to hate getting caught in these areas called the doldrums because it's so boring, because they wouldn't go anywhere. And these sailors would get bored and, I guess, fight and be unrest. And also, when they were at sea for so long, and they were caught in these areas of no wind, the doldrums, for so long, their minds started to get a bit crazy, and they were starting to hallucinate and dream and imagine of things that weren't always there. So, of course, these sailors, these men, had left their wives and girlfriends on land at the ports and hadn't seen them for many months or many weeks. So they started to miss their wives, miss their girlfriends. So what happened was they started looking out at the sea, as what else are you going to do but look out at the sea and watch the ocean. And they started seeing these animals, these ocean animals around the boats. And they started seeing these sea lions and these larger animals. And because they're a little bit crazy at being at sea for so long, that they started to imagine these sea animals as beautiful creatures, beautiful women. So this is where the idea and notion and myth of mermaids came from, was the misconception and the craziness of these sailors thinking that these animals were these beautiful women. And mermaids, that's where it came from. Now focus on the areas of high pressure around 30 degrees north and 30 degrees south, looking at what's called the horse latitudes. So this area is called this because of a certain reason. Now, ever since humans crossed the Atlantic to either seek out new lands or seek out new trade routes, try and trade goods from each area, furs and tobacco and timber and silk and spices, you also had the movement of horses. Now, the American colonies and the growth of America had a lot of farmland and land that had to be worked by horses. Now, horses were indigenous to America previously, but there was a large import of horses from Spain, the Middle East, where they brought over thousands of horses to aid the development of 13 colonies and also these areas to farm in America, when America became a lot larger and a lot stronger in the 1800s. So they would transport these horses by ship. Now again, just like the equator and the doldrums, the 30 degrees north and south is an area of high pressure, so the air is going to sink down and then be moved north and south of that sinking pressure. But the actual location and latitude of 30 degrees north and south, you experience limited or no wind. So when ships would sail from America or from Europe towards this area of the ocean over 30 degrees north and south, you'd experience a slowing down effect, and unfortunately boats get caught in this for a long time. It's the same as the doldrums. Now, these ships only have a certain amount of rations, both food, water, and perhaps alcohol for these sailors, and if the boat was stuck in these horse latitudes where there's no wind, then all the rations and supplies would be used. And what's left? Well, rather than go to starvation, the horses were used as food, which is horrible because it's a beautiful animal and they're amazing, but it's either starvation and death or eat the horse. Or the other version was a lot of these boats would push the horses off into the ocean to make the boats lighter, so more chance of being moved by the ocean currents, and to get out of these areas of no wind, which is because of the high pressure and the sinking air, as seen by the diagram. So the horses were kind of like the last thing to be eaten or last thing to be gone, because they were a high value good that they were transporting from Europe, let's say, to America. So again, these areas were called the horse latitudes. So we discussed the three cells, discussed the pressure belts that are created because of these three cells. We discussed the winds, the surface winds that you see on the diagram. We discussed the doldrums and the ITCZ and what it is. We discussed the horse latitudes. Now we've got to discuss the winds. Now the winds are called certain names based on where they originate from, where they come from. So if you're looking at a compass and you have north, south, east and west, you can see which way these winds are coming from. So that's how they are named. For example, the winds either side of the equator that converge to form the ITCZ, they are the trade winds. Now these are easterlies. They come from the east and go to the west, both on the northern hemisphere and southern hemisphere. So these are called the trade winds, but they are easterlies. Now the winds that go from 30 north to 60 north, and the same in the southern hemisphere, for the Ferrel cell, these are called the westerlies because they start in the west and move to the east. They are westerlies. They are named from where they start from. So they are called the westerlies. Now, the winds in the northern and southern poles, these are called the polar easterlies, from 60 south and 60 north up to 90 north and 90 south. So this area up here around the polar regions, the Arctic and Antarctic, these are called the polar easterlies. They start in the east and go west. And these form the global wind system as part of the general circulation model with the Hadley, Ferrel, and polar cells. So as a summary or conclusion, this review video is looking at the incoming solar radiation causing differential heating on the Earth's surface through the troposphere, through thermodynamics, and that creates differences in temperature, then pressure, and air rising, air descending, causing high and low pressure across the Earth's surface and the globe, creating GCMs, pressure belts, and finally looking at the global winds, including the westerlies, easterlies, the doldrums, the horse latitudes across our atmospheric system. Thank you so much for watching the video. I hope you enjoyed it. If you like it, please subscribe and maybe hit the like button. If you like more on this content, please check out my channel, which has all these videos on earth science.